All right, let's go through the 2004 electromagnetism free response question number 1 here. And this is from 2004. It says, here we've got a conductor, we've got a lambda here. We're looking at, I'm just kind of checking out the picture. Got 3 different regions, got these different points. This is a conducting material. That's really important. It says the figure above left shows a hollow, infinite, cylindrical, uncharged conducting shell. It's uncharged. Of inner radius R1 and outer radius R2. An infinite line charge of linear density lambda, so its positive lambda, is parallel to its axis but off center. In a large cross section of the cylinder, the shell is shown above right. Okay, so on the cross section above right, I sketched the electric field lines, if any, in each region, 1, 2, and 3, and then use plus and minus signs to indicate any charge induced on the conductor. Okay, so think about this. We've got this conductor, but it is it's off center. It's obviously closer to this side of the conductor than this. So this infinite, this charge, this lambda, it's got positive charge on it. And obviously if I surround this with a Gaussian surface, you're going to see electric lines of flux go through that. I mean, this has got a charge. So we have positive charge. Now, if I drew a line of charge, it kind of goes like this. It's going to start at the positive, but it's going to terminate at the surface of the conductor, right? Conductors in electrostatic condition can't have an electric field in it. So this field line is going to go here and terminate here, and that's going to draw a negative charge to the surface here. So put an arrow on it, and then you can put that negative charge. Now this is a conducting surface, so let's draw another one. And so we'll come up here, but you can't just, don't do this. You can't just have a straight line like that. Why? Because electric field lines either start or terminate at the surface of a conductor perpendicular to that conductor. Okay, so it's gonna, that's something that we talked about. So it's gonna curve a little bit. Curve a little bit. Okay. And it's going to be symmetric. But notice that, see here, the charge is closer over here. So it's the electric forces drawing negative charge to the inside surface are going to be stronger than over here. So these things are going to start spreading out now. They're a little farther away. So it's going to, the electric field is not going to be quite as strong farther away. And make sure that you show them those electric field lines terminating in a perpendicular to this surface. So in other words, this should be a 90-degree angle right in here. Okay, and then I'll just start drawing more field lines. Doesn't really matter how many you draw, as long as you just want to draw enough to show the space. That's probably enough so that the electric field lines get farther apart. Out here they're more spread out. Over here they terminate in a way that's perpendicular to that surface, and they're more crowded over here. Now so that takes care of the inside surface. But look what I've done. I've drawn 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh yeah, I drew 9 charges there. So I have to have, since the conductor is electrically neutral, if I draw 9 units of negative charge here, there has to be 9, lines of flux out here. So, although you draw the negative to the inside surface, on the outside surface, there's no electric field inside the conductor, so you just have a charge out here, and those charges are going to push each other around so that they're evenly distributed. So 1, 2, 3, 4, 5, oh wait, 6, 7, 8, 9. I put those a little bit more crowded, but one thing you can do, you can put evenly distributed if you meant to draw that. So these field lines are going to come off straight like this, perpendicular to the surface, and you should have just as many lines of flux on the outside as you drew on the inside. These should be more crowded over here, but out here they should be as evenly distributed as you can draw them, and just going straight off into infinity. Okay, and now in the spaces below, rank the electric potentials of at points A, B, C, D, and E from highest to lowest. 1 is the highest potential. So 1 has the highest potential. If the 2 points are the same potential, give the same number. Give the same number. Okay. So, well, take a look. If I'm infinitely far away, let's say my finger here represents a place that's really, really far away. We have 0 voltage, and then I'm going to push my positive test charge against the electric field. So I'm gaining potential, gaining potential, gaining potential, until I get to A. So A is farthest away. It has the least amount of potential. Then once I go inside the conductor, there's no electric field in here. So as I move inside the conductor, my potential isn't going to change, which means B and E are going to be at the same potential. Then I'm going to go into C. Now I'm working against the electric field to get from this inside surface to C. So I've gained potential, and then I've got the most potential closest to this charge, this lambda charge here. So that means that D has the greatest potential. So V at D is number 1. Now let's go out. That means C has the second most potential. And then I come out. Now B and E both have the same potential. So they have 3, 3, 3. And then, of course, A has the least amount of potential, so we'll call it number 4. So that's how you do that one. Okay, now let's go to the next page. It says the shell is replaced by another cylindrical shell that has the same dimension. It's down here so you can see it. But is non-conducting. So now we have a non-conductor and carries a uniform charge density of rho. The infinite line charge, still of density lambda, is located at the center of the shell. So now we've moved it to the center. Using Gauss's law, got to use Gauss's law. No memorized equations, derived equations. You have to start from there. Calculate the magnitude of the electric field as a function of the distance r from the center of the shell for each of the following regions. Express your answers in terms of the given quantities and fundamental constants. Okay, so r is less than r1, so when we're inside here. So we're going to surround this guy with a Gaussian surface, but remember it's a cylinder, so I'm going to kind of draw a cylinder like this. And you got to start with Gauss's law. When I surround a charged, some kind of charge distribution with a surface area, I want that surface area to match the symmetry. It has cylindrical symmetry. And that'll be equal to the charge enclosed by the Gaussian surface divided by the epsilon naught. So, this is Gauss's law. So E time. Now the area of this is 2 pi r times the length. 2 pi r times, and I'll just call this L. 2 pi r times the length. Now remember, we never integrate the left side of Gauss's law. Now we have to figure out how much charge is enclosed. Well, I've got this lambda in here, and it's a uniform thing, so it's just lambda times L. The charge per unit length times the length gives us the total charge over epsilon naught. And so the L's cancel. And now I can solve for, so we want the electric field. So the electric field is just going to be lambda over 2 pi epsilon naught times 1 over r. And notice what I try to put all the constant stuff in, and the variable r kind of separate from it. And there's the magnitude. And it just wants the magnitude of the electric field. I don't need to put a unit vector with that. Okay? So that's just a very standard Gauss's law problem. It doesn't get easier than that one. Now, what if we're between R1 and R2, like in here? Well, now if I draw a Gaussian surface for this guy, now how much charge is enclosed by that Gaussian surface? So I'll just, to be complete, charge enclosed over epsilon naught. So this is just the same thing, E 2 pi RL. That's the surface area of my Gaussian cylinder. But how much charge is enclosed? Well, we still have lambda L. We still have the charge in there, but now we've got the fraction of this area. Let's put our epsilon naught there. The fraction of the area, it's the fraction of the volume. So we want rho, and we want, what is the volume of this? Well, it's the volume of a cylinder. So the volume of a cylinder is pi r squared L. Okay, so that's the now that would be the volume of the whole cylinder, but we have to subtract out this hole that's in it, right? This part here, the shaded part, has charge, but this white part here, there's no charge in there. So we have to subtract it. So that's going to be minus pi, and this has a radius of R1 times L. And this awkward expression right here, this is the volume of that hollow cylinder that has charge on it, and because I've subtracted out the whole, and then this is just that lambda part. All right, so let's simplify. E equals, what can I pull out of here? I can pull the L out. Oh, well, first of all, the L cancels. Let's just cancel it. And then, so this is just going to be lambda plus pi times rho times r squared minus r1 squared all over 2 pi r. So we got an r here and an r here. It's kind of a complex expression, I guess. And I think I'll just leave it there. Not sure what the solution guide did with that, but that's where I'm going to leave it. Now, and then of course outside, we want to know was, so now I'm just going to surround it by a Gaussian sphere that's on the outside of this thing. And same expression. And I probably don't need to do that, but I'm just a little, I like doing that. All right, so this is going to be E times 2 pi RL. Notice that this is the same. And now the charge that's inside is just lambda L plus rho times pi R. Now, once you get, let's take a look at this picture. Here's R. As I go out like this, and then here's R. Now, once I get past R2, there's no more charge. So I can just stop when I get to R2. So it's R2 squared minus pi R1 squared and times L. This is the volume of the stuff that has charge in it. And then I'm going to divide all of that by epsilon naught. So the length of the Gaussian surface cancels, and I divide by 2 pi r. So E equals lambda plus rho times rho pi r2 squared minus r1 squared over 2 pi epsilon naught over r. I guess I could pull that 1 over r out like I did before, but I don't know. I'll see with that. Don't spend too much time simplifying expressions. They'll give it to you. Okay, and so there we go. That's part C. I don't think there's a part D. Oh, good. Thank goodness that's over. And that is how you do. That's what. Obviously, the big idea is for this is just how to use Gauss's law, and make sure that this is the area of the Gaussian surface. You will never integrate this side because you're going to choose a Gaussian surface where E is the same everywhere. So it's just the electric field times the area. The area equals the charge enclosed by your Gaussian surfaces. And this is where the challenge is going to be. And if you're going to have to integrate, to find that charge, although we did not have to do that this time because very nicely this charge density was not a function of R, it was just uniform. It was just a constant rho. And the same thing is true with this lambda. So it was actually kind of a nice, straightforward problem for once from the College Board. Thank you, College Board. Okay, if you have any questions, bring them to me or leave them in the comments of this video, and I'll try and get back to you. That is all.